This video is about continuity. If you appreciate the content, please give it a like. Basically, a function is continuous if it is unbroken. If there is a break in the graph at c, we say f of x is not continuous at x equals c. Or we can say that f of x is discontinuous at x equals c. Or we can say that f of x has a discontinuity at x equals c. Basically, a discontinuity is a break in the graph. There are two types of discontinuity, removable and non-removable. A removable discontinuity is a hole in the graph, a single missing point. You get a removable discontinuity at x equals c when there is a factor of x minus c in the denominator that is completely canceled out by another factor of x minus c in the numerator. Notice that in this example, the original function f of x is equivalent to the line x minus 4, except for the domain restriction that x cannot equal c, thus the hole. Here's a key feature of a removable discontinuity. If f of x has a removable discontinuity at x equals c, the limit as x approaches c exists. In other words, the limit as x approaches c from the left is equal to the limit as x approaches c from the right. The other type of discontinuity is a non-removable discontinuity. This can either be a vertical asymptote, or it could be a jump. You get a vertical asymptote at x equals c when there's a factor of x minus c in the denominator that does not get canceled out by a factor from the numerator. You will get a jump discontinuity from a piecewise function where the pieces don't connect. Whether it's a vertical asymptote or a jump, we say f of x has a non-removable discontinuity at x equals c. If f of x has a non-removable discontinuity at x equals c, a key feature is that the limit as x approaches c does not exist, whether because the limit is infinity or because the limit from the left does not equal the limit from the right. The formal definition of continuity has three parts to it. F of x is continuous at x equals c if and only if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x, which is equal to the value of f at c. This is a key concept. Memorize this. If you are asked to discuss the continuity of a function, they are asking you to do two things. Number one, they are asking you to classify each discontinuity as removable or non-removable. And number two, they want you to say where f of x is continuous. Remember, a removable discontinuity is a hole. An asymptote or a jump is a non-removable discontinuity. So we begin by saying f of x has non-removable discontinuities at x equals -1 and x equals 2. Then we add f of x has a removable discontinuity at x equals 3. Finally, we conclude by saying f of x is continuous everywhere else. That's how you discuss the continuity of a function. If you are not given a graph, you need to use your pre-calculus skills to identify holes and vertical asymptotes. The factor of x plus 3 in the denominator that's canceled out by another factor of x plus 3 in the numerator means we have a hole at x equals -3. In other words, g of x has a removable discontinuity at x equals -3. The factor of 2x minus 1 in the denominator that does not get canceled out by anything in the numerator means g of x has a vertical asymptote at x equals 1/2. So g of x has a non-removable discontinuity at x equals 1/2. And don't forget to mention that g of x is continuous everywhere else. Each piece of this piecewise function is continuous on the corresponding interval. So we just have to figure out if there is a discontinuity at the value where f of x changes from one piece to the next. In other words, is there a discontinuity at x equals -2, x equals 1, or x equals 4? On the AP exam, you will often get free response questions like this. Is f of x continuous at x equals -2? Justify your answer. You have to justify your answer using limits. Remember, f of x is continuous at x equals c if and only if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x, which is equal to the value of f at c. As x approaches -2 from the left, the 2x plus 8 piece applies. So we begin by finding the limit as x approaches -2 from the left of 2x plus 8. We can find this by direct substitution. So that'll be 2 times -2 plus 8. That's -4 plus 8, which is 4. As x approaches -2 from the right, the 2 minus x piece applies. We can find the limit as x approaches -2 from the right by direct substitution. So this will be 2 minus -2, which is really 2 plus 2, which is 4. So far we have proven that the limit as x approaches -2 exists because the limit from the left is equal to the limit from the right. They are both equal to 4. However, to prove that f of x is continuous at x equals -2, we must also show that the value of f at -2 is also equal to 4. At -2, the piece that applies is the 2x plus 8 piece because this piece applies when x is less than or equal to -2. So we can evaluate f at -2 by plugging -2 into this piece. 2 times -2 plus 8. And yes, this is -4 plus 8, which is positive 4. We conclude by saying f of x is continuous at x equals -2 because the limit as x approaches -2 from the left of f of x is equal to the limit as x approaches -2 from the right of f of x, which is equal to the value of f at -2. f of x switches from 2 minus x to the square root of x at x equals 1. So on an FRQ, you might be asked, is f of x continuous at x equals 1? Justify your answer. To find the limit as x approaches 1 from the left, we use the 2 minus x piece. We can do direct substitution. Plugging in 1 for x, we get 2 minus 1, which is equal to 1. To find the limit as x approaches 1 from the right, the square root of x piece applies. Again, we can evaluate this limit by direct substitution. The square root of 1 is also 1. So far we have proven that the limit as x approaches 1 exists because the limit from the left is equal to the limit from the right. However, to prove that f of x is continuous at x equals 1, we must show that the value of f at 1 is also equal to 1. Which piece applies at x equals 1? I'm looking for the little or equal to sign at x equals 1, but neither has the or equal to sign. That means f of x is actually undefined at x equals 1. We conclude that f of x is not continuous at x equals 1 because f at 1 is undefined. But what type of discontinuity is this? Since the limit from the left was equal to the limit from the right, f of x was approaching the same output value from both sides. The fact that f right at 1 was undefined means there must be a hole at that transition point. In other words, f of x has a removable discontinuity at x equals 1. The last place where f of x might have a discontinuity is at x equals 4. So the question becomes, is f of x continuous at x equals 4? Justify your answer. To find the limit as x approaches 4 from the left, we use the square root piece. We can evaluate this limit by direct substitution. Plugging in the 4 for x, we get the square root of 4, which is equal to 2. To find the limit as x approaches 4 from the right, we use the 3 over x minus 4 piece. However, we can see that if we were to do direct substitution, we would get 3 over 0. Do not write equals 3 over 0 at any point in your work. Never write down an undefined expression. You will lose the point. Instead, use arrows like this. The numerator is approaching 3, of course, while the denominator is approaching 0. So the limit does not exist. We can already tell that f of x is not continuous at x equals 4 because the limit as x approaches 4 from the right of f of x does not exist. But what type of discontinuity is this? We saw that the limit as x approaches 4 from the left was 2, but the x minus 4 in the denominator of this piece means that there is a vertical asymptote at x equals 4 as x approaches 4 from the right. So this is a non-removable discontinuity. Part D of this FRQ might say, discuss the continuity of f of x. We previously found that f of x had a removable discontinuity at x equals 1. We just found that f of x has a non-removable discontinuity at x equals 4. We conclude by saying f of x is continuous everywhere else. Discuss the continuity of the function f of x equals the cotangent of 5x minus pi over 3. In pre-calculus, we learned that many trig functions have vertical asymptotes. We now know that these are non-removable discontinuities. We know that cotangent is equal to cosine divided by sine, so f of x is equal to this. We also know that a trig function will have a vertical asymptote wherever the denominator is equal to 0. You can't divide by 0. So f of x will have a vertical asymptote wherever the sine of 5x minus pi over 3 is equal to 0. In other words, the solutions to this equation will be the locations of the discontinuities, the non-removable discontinuities. To solve a trig equation, you first solve for the expression on the inside. So, where is sine equal to 0? Sine is the y value on the unit circle, and y values are equal to 0 here and here. So that's at 0 and pi. Be careful, they did not give us a domain limitation like the interval from 0 to 2 pi. So we're not going to just make a list of solutions. We need to somehow write an expression to represent the infinitely many solutions. The first solution is at 0. To get to the next solution, you would have to add pi radians. And in fact, every time you add pi radians, you get to another solution and another and another. So we can get infinitely many solutions by adding multiples of pi. In other words, by adding pi k, where k is any integer. Now we just have to solve this equation for x. We begin by adding pi over 3 to both sides of the equation. On the right-hand side, we are just adding 0 plus pi over 3, which of course is pi over 3. So now we have 5x equals pi over 3 plus pi k, where k is any integer. To get x by itself, we need to divide both sides of the equation by 5. However, when we divide two terms by 5, it's the same as dividing each term by 5 like this. Quick side lesson here. A over b divided by c is equal to a over bc. So when you divide a fraction by something, whatever you are dividing by ends up multiplying into the denominator. Similarly, pi over 3 divided by 5 is pi over 3 times 5, which is exactly what we see right here. So on the next step, you're going to see pi over 15. This is the expression representing the infinitely many solutions to this equation. So we can now say f of x has non-removable discontinuities at x equals pi over 15 plus pi over 5k, where k is any integer. Don't forget to add f of x is continuous everywhere else. Again, we know the discontinuities are non-removable because dividing by 0 like this leads to vertical asymptotes, which are non-removable discontinuities. Discuss the continuity of the function f of x equals the absolute value of x minus 4 over x squared minus 16. First of all, x squared minus 16 is the difference of two squares, which factors like this. Do not think you can just cancel out these x minus 4s. One of them is inside of absolute value, and absolute value is actually a piecewise function in disguise. Quick side lesson, the absolute value of x is sometimes equal to x, and it is sometimes equal to the opposite of x. If x represents a positive number, then the absolute value isn't really doing anything. So we can just take away the absolute value without changing the value of the expression. In other words, for x greater than 0, the absolute value of x is equal to x. However, if x itself is negative, then this top equation becomes false. The absolute value of x, of course, is positive, but x itself is negative, so these two cannot be equal. When x is less than 0, we need to put an extra negative sign in front of the x to turn it positive again, which will then equal the absolute value of x. This is what I mean when I say the absolute value function is really a piecewise function in disguise. Similarly, the absolute value of x minus 4 will equal x minus 4 if x minus 4 is positive, and it will equal the opposite of x minus 4 if x minus 4 is negative. Adding 4 to both sides gives us x is greater than 4 or x is less than 4. We can rewrite f of x without the absolute value symbols by splitting it into a piecewise function. F of x will equal this blue expression if x is greater than 4, and it will equal this red expression if x is less than 4. If x is greater than 4, x minus 4 is a positive value, so we can take away the absolute value symbols without changing the value of the expression. However, if x is less than 4, then x minus 4 is a negative value, so we need to put an extra negative sign to turn it positive again. Canceling out the common factors of x minus 4, we find that f of x is equal to 1 over x plus 4 if x is greater than 4, and negative 1 over x plus 4 if x is less than 4. By the way, because of the factor of x minus 4 in the denominator, we know that f of x is undefined at x equals 4. That's why you don't see an or equal to sign on either one of these pieces. We just need to figure out whether this discontinuity is a removable or non-removable discontinuity. Is this going to be a hole or is it a jump? To figure that out, we need to see if the limit as x approaches 4 from the right is equal to the limit as x approaches 4 from the left. As x approaches 4 from the right, the top piece of this piecewise function applies. We can find this limit by direct substitution. So this will equal 1 over 4 plus 4, which is 1 over 8. As x approaches 4 from the left, the bottom piece applies. We can again find this limit by direct substitution, but this time we get negative 1 over 8. As x approaches 4 from the left, f of x is approaching negative 1/8. As x approaches 4 from the right, f of x is approaching positive 1/8. This is a jump discontinuity, a non-removable discontinuity. So far, we have found that f of x has a non-removable discontinuity at x equals 4. That takes care of the factor of x minus 4 in the denominator. Because of the factor of x plus 4 in the denominator, we know there will be some type of discontinuity at x equals negative 4. Specifically, we know that there will be a vertical asymptote at x equals negative 4 because we have a factor in the denominator that will never be canceled out by anything in the numerator. A vertical asymptote is a non-removable discontinuity. So we can say that f of x has a non-removable discontinuity at x equals 4 and x equals negative 4. Don't forget to conclude your discussion of continuity by adding f of x is continuous everywhere else. Let's do one more. Find the value of b that would make f continuous for all real numbers. We know for f to be continuous at x equals c, the limit as x approaches c from the left must equal the limit as x approaches c from the right, which must also equal the value of f at c. The only place where f of x might not be continuous is at x equals 5. So we need to find the value of b that will make f continuous at x equals 5. In other words, we need to find the value of b that will cause the limit as x approaches 5 from the left to equal the limit as x approaches 5 from the right. As x approaches 5 from the left, the top piece applies. Be careful, we cannot evaluate this limit by direct substitution because we would get 0 in the denominator. So we need to use one of our other techniques. Let's try rationalizing the numerator. Remember, we would do that by multiplying by the conjugate. We have 2 minus radical x minus 1, so the conjugate will be 2 plus radical x minus 1. To keep it legal, we need to multiply by the same thing in the denominator. That way, we are really multiplying by 1, which will not change the value of this expression. The beauty of multiplying by the conjugate is that a minus b times a plus b is always equal to a squared minus b squared. So let's use that shortcut. A is 2 and b is x minus 1. So when we multiply by the conjugate, we will get a squared, which is 4, minus b squared, which is x minus 1. Squaring a radical makes the square root go away. I don't feel like rewriting this whole thing just to distribute the minus sign, so I'm going to take away the parentheses and turn this into a plus. But be careful, a common mistake, a really common mistake, is for students to not put parentheses around the x minus 1 and not remember to distribute the negative sign. So if you put this, you're stuck and the whole problem is wrong. Instead, it is this. We now have these like terms. 4 plus 1 is 5. So on the next step, in the numerator, we're going to have negative x plus 5. So now we have this. When I have a negative leading coefficient, I like to factor out that negative sign. So on the next step, we will have negative x minus 5, like that. I just realized that I've been making a really bad mistake. This is a limit. So at every step of this problem, I should have been writing the limit as x approaches 5 from the left. So I'm going to go back and squeeze that in. So my work should be looking like this. Now we notice that we have a factor of x minus 5 in the numerator and in the denominator. We can cancel out this common factor without changing the limit. We can evaluate this limit by direct substitution. When you do the direct substitution, you can finally stop writing the limit as x approaches 5 from the left. Plugging in 5 for x right here, we have 5 minus 1, which is 4. The square root of 4 is 2, 2 plus 2 is 4. So the limit from the left is negative 1/4. Luckily, we can find an expression for the limit as x approaches 5 from the right by direct substitution. Plugging in 5 for x right here is going to simply give us 10 plus b. If f is to be continuous at x equals 5, the limit from the left must equal the limit from the right. In other words, 10 plus b must equal negative 1/4. We just need to solve for b by subtracting 10 from both sides. So b will equal negative 1/4 minus 10. Let's go ahead and clean this up by making like denominators. This is like 10 over 1. So I am multiplying by 4 over 4 in order to make like denominators. So b equals negative 1 over 4 minus 40 over 4. So the value of b that makes f continuous is b equals negative 41 over 4. This is what you would see as an answer choice on a multiple choice question, but to be clear, if this was a free response question, I would recommend just leaving your answer like this. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.